Alright, boys and girls, welcome back to the drive-thru on to 2-4. Alright, so now that you've seen that there are contexts for continuous exponential functions, it's a good idea to start thinking about the numbers that fill in between 2 to the second and 2 to the third. So this is just weird math, but it's going to matter. 2 squared is 4. 2 cubed is 8. So what is 2 to the 2.5? Is that 6? It's probably close to 6, right? And that's what we're going to be talking about here in this chapter. So let's complete the table. F of x, I'm just going to make this bigger in case you can't see it. Hopefully you have your paper in front of you. It's 4 times, excuse me, I like to write it like this, 2 to the x. These are the same thing. Alright, so that just means we've got to do 2 to the x first, then multiply it by 4. So 2 to the first is 2. 2 times 4 is 8. 2 squared is 4. 4 times 4 is 16. Alright, got it. We're multiplying each one by 2, but let's just make sure we have that right. That's what that indicates, so I know that this is going to be 2, but 2 cubed is 8. 8 times 4 is 32, and so the next one will be 64. So it wants us to graph those on the final page. So 0, 4, 1, 8. Just keep doubling them. I can remember that. So 0 was 4. 1 was 8. 2. Oh, that's not. Sorry. 1 is over here. I got my little thing covering up. 1 is 8. 2 is 16. 3 is 32. Finally, 4 is 64, which is going to be off of our sheet somewhere up here because I couldn't copy it all. So this is great. It really gives you an in-depth look of how this is changing. Okay? Let's try to make this as smooth of a curve as I can make it. Maybe you just decided to use Desmos, and if so, that's great. Okay? Alright. Well, we might need that for some of the rest of our... Alright, so plot these points on the graph at the end of the task. We just did that. Let's say we wanted to create a table with more entries, maybe a point halfway in between each of the points on the table above. There are a couple ways that we might look about it. So Travis says if the function doubles each time, half the growth occurs between 0 and a half, and the other half occurs between a half and 1. So for example, at x equals 3/2 by finding the average of the outputs at the 0 and the 1. So here's what they're saying. It's exactly what we said before. If this was 8, and this is halfway in between here, then halfway in between 4 and 8 would be 6. 4 plus 8 divided by 2 equals 6. Well, we know all the even ones. This one's 16. This is 32. And this is 64. So what's halfway in between 8 and 16? Let's see. 8 plus 16 is 24 divided by 2. That's going to be 12. What's halfway in between 16 and 48? That's going to be 24. What's halfway in between 32 and 64? That's going to be 48. And you can see we have actually a nice consistent growth here. When you cut them in half, up 2, 2, up 4, up 4, up 8, up 8. Okay? And so now they want us to plot those points. Let's see what it says. Also plot Travis's data on the graph at the end of the task. So Travis's data was 1.5. Let's see. 1.5. Well, half was comma 6, so Travis's data was right there. That's pretty close. This was at 8. And then, let's see. I got to go back. Next one was 12. Is that right? 12, and then 24 and 48. 12, 24. So at this one, we're going to go to 12, which is here. That's pretty close. At this one, we're going to go to 24. That's here. We're all over it. Sorry, that should be here. And then here, this will be 48. 48, 5, 6. Oh, yeah. I like the way that looks. So I'm not going to continue to graph them because it's just going to get messier, but let's continue to do what they want us to do. Fill in the parts of the table below you've already computed, and then decide how you might use Travis's strategy to fill in the missing data. Also, we did that already, so we already did this. I don't know why. I think I copied it twice. I think this reasoning works for exponential continuous functions. Okay? I notice the function increases by the same factor each time x goes up by 1, and I think this is like the geometric meanings. It seems like this property should hold over the half interval as well. I don't think we need to do this in number 5 too much. Let's just skip on to number 6, okay? What if Miriam wanted to find the values of the function every third of the interval? So let's go back to what we started with. Sorry, we know that the whole numbers went 8, 16, 32, 64. So 8, double it again, 16, double it again, 32. Well, what if we wanted like a third way point? So if you just thought about 4 on a number line, 5, 6, 7, 8. Okay, there are 1, 2, 3, 4 spaces in between. Well, if we wanted a third, 4 divided by 3, it would be somewhere around there. This would be a third, and then another third, and then another third. So we're going to call it like 5.1. and then 6.7. These are just guesses. So then if we went from 8 to 16, let's see, we got 9, 10, 11, 12, 13, 14, 15, 16. All right, so a third of the way. How many spaces are there? 1, 2, 3, 4, 5, 6, 7, 8. A third of 8 is a little less than 3, so it'll be here. And a little less than 3. 1, 2, 3. It'll be about here. So I think we're like 10.7 and 13.5. Okay. From 16 to 32, there are 16 spaces. And so 16 divided by 3 is a little more than 5, so we'll just do that in our head. It's going to be 21.2. And add 5.2, we'll call it 26.4. And I honestly don't know what we're doing here, but I'm just doing it. I'm going to trust that this will make sense later in the homework and in the section. I think that's good enough. Let's do some homework. Boom!